Good. Okay, good morning. Today we're going to change topic, introduce new topic. So far we've just seen technicalities about arrays and so on, and a little bit of a demo code, a couple of demo codes. Before we introduce the new topics, are there any questions about what we've seen so far? I'll just remind you that whatever question, doubt you may have, whatever, just you can write on the forum, okay? I've seen that nobody has written there, but it's there for that purpose, and you can even write anonymously, and so just reminding you of that. We're still waiting to know whether we will use Piazza or not. For some reason, the interaction is much, much better when using Piazza, and students like it a lot more than Blackboard Forum. I mean, it's understandable why, but the functionality really is there. So if you have a doubt, just use the Blackboard Forum, okay? Next, new topic. So the new topic is actually optimization problems. Okay, so this is a topic, actually, it's an overarching topic, as I mentioned in the first lecture, that will accompany us almost to the end of the course, okay? So let's then try to introduce what it is all about. It's a vast, vast topic, okay? And just to be clear, we are not going to cover, and we're only going to scratch the surface. So, and use it as an excuse to write some interesting, hopefully interesting codes. So I'm sure that everybody has at least some intuitive idea of what an optimization problem is. You have something that you're controlling, you want to find the way to, say, to optimize it in some way, which meaning achieving some best score of some sort, okay? So, of course, in order to make progress, one needs to be more precise about what one is trying to do, and start getting into modeling and using maths to describe what we're actually really precisely trying to do. So there are a ton of different situations that can fall under this umbrella. We'll start from trying to describe something general, but just for definiteness, consider a silly example, which we're actually just use right now, but just to give a sort of idea, okay? Just to set idea. So say that, for example, you are, I don't know, you are administrating some sort of company, let's say, and it's going to be very silly and simplified, but just for the sake of it, and say that you have a budget to allocate, and say that you have just to decide how much to use for production and for, I don't know, administration, admin, and then marketing. Say, for example, just, okay, and then you have the budget, and of course, that means that you can, say, have production from 0 to some maximum budget, and the same for the others, okay, something like this, and therefore, you are now sort of working inside this space, okay, this little cube here. But of course, also, if you allocate everything for production, then nothing is left for anything else. And so actually the space of what you can really do is something like this. So you have a surface like that triangle over there. I hope that's clear. Okay, so if you allocate all the budget for production, then it's a 0 for everything else, and so on. And the maximum is, I mean, the sum of the three must always be whatever you have at your disposal. And now in this picture, a point here, let's say this one, okay, here, well, any point in this space is one possibility that you have, okay? So one choice that you can make, one configuration. And then maybe, I don't know, something here, I'm just pictured it completely at random, so don't take me seriously in any way. This might be the one that gives you the best profit, for example. Say, so this one is best. So say that you want to maximize the profit, and you're looking at the whole space of your possibilities, and you're trying to find the best. Okay, so I think that this is intuitive enough. So as an example, a couple of things. Of course, as you can see here, we are now working in a three-dimensional space, which is exactly the same as the number of parameters that we are able to manipulate. Of course, this is a super simplified scenario. In a realistic scenario, you would have, I don't know, hundreds possibly of these, and therefore it means that you will be working in a 100-dimensional space or something like that. Okay, so very rapidly we get to high-dimensional spaces that we cannot even visualize. And we are working inside there. Okay, so this is one thing that I need to point out. Then let's try to put down some notation. Okay, some notation is, let's say, so now using this as maybe some sort of inspiration, we will say that capital X, curly capital X, this is, I mean, oh, sorry. I have the slides here. So, okay, so here is where we define things. Okay, so this capital X is the space of configurations. Okay, the space of configuration, in the example, it's a triangle, which is also called the simplex because it can be arbitrarily dimensional. Now, X, small x, which is one of the possible configuration is, I mean, it's one element of this other set, is a configuration. And so, given the example, you see that this X could be something like a three-dimensional vector in this example with some particular constraints, but it's, in general, it's going to be, say, n-dimensional thing, okay, with all the choices that you made for all the parameters that you have. Okay, and then we have a function, which I'm going to call C for cost, which given any point in the space gives you a value, okay? And this is going to be the cost. And the goal, minimize C, which means find argmin, so the argument that minimizes the function C over all possible x's that are allowed, okay? Now, in the example I just said that we were trying to maximize a profit, for example. Here I'm saying we're minimizing a cost. Of course, C is just a mathematical function. If you take the profit and change its sign, and then you can minimize the negative profit, which is, you call it the cost, okay? And that's, so this shows immediately that whatever problem you have, if you have a maximization problem, you can always take the function that you're trying to maximize, just change its sign and do a minimization problem instead. So from now on, we are going to speak about minimization problems with the understanding that they are just, maximization problems are just the same, and you solve them exactly the same way, okay? You just need to remember to switch the sign of your function. Okay, so this is it. Okay, now, as I briefly mentioned, this kind of example that we are looking at right here is it's a very important class of optimization problems, but it's not what we are going to see during the course, because that they are, in a sense, they are too advanced from the point of view of programming. So there are specific tools to deal with exactly this situation, and actually something even more complicated than that. It's called linear programming. It's very important, it's very interesting. I think that there's a course by Professor Borgonovo that treats this. It's an optional course that treats this if you want to learn about that. But the programming tools that you use to solve that are, let's say, that would take us too far away from our course and would not really teach us too much in terms of actual programming. Okay, there are library implementations. There are people who created code to do that, which is incredibly efficient and even almost, let's say, magical in how fast it can perform, how quickly. Exactly because it's such an important problem, people have worked really, really hard in trying to optimize it as much as humanly possible, and then a little bit more. So, so we're not going to deal with that, but in the second half of the course, we will see a situation similar to that, just that in which there are not going to be constraints. There are not going to be constraints on the space X, but the cost function is going to be complicated. Okay, so that's going to be an interesting case that we will have a look at in the second half of the course, in particular with Professor Iozzi. Right now, we are going to use this same framework, but in a different case. Okay, the case is that we're going to look at discrete problems. So this that I wrote here, this notation and goal, as you can see, is very general. I haven't said anything at all about what this capital X might be. And in particular, here's an example that I think should be familiar to most of you. Suppose that you have a graph, okay? You're given a graph of some sort, probably with, I don't know, with some weights on the edges, and you're also given a starting point, let's say this one, start, and you're given an endpoint here. Does this bring anything to mind? So what's the optimization problem here? Find the shortest path from the start to end, of course, or the best path from start to end according to some metric, which is probably the shortest one would be, say, a typical example. And I think most of you know how to solve this. I mean that there's an algorithm to solve this, right? Am I right? Yes, good. So Dijkstra's algorithm, you can use it to solve this problem. Now, let's map now. Let's think about what is this, in this case, our space of configuration. What is a configuration in this example? What, sorry? Exactly. So one configuration is one of the possible paths. A path with the additional restriction that it must start at the input and I mean start somewhere well-defined shortest path. No, okay, so TSP was an answer that I hadn't seen, but we are actually going to see TSP later. Now this example here, so a configuration could be something like this, one possible configuration, another possible configuration, of course, could be something like this. Maybe go here, maybe also come back here, and then go here. Okay, so of course the orange one is not going to be very good if you're taking a detour there, but it's one of the possibilities. Okay, so so here X is a path from A to B, well, from start to end, sorry. So these are all paths from start to end. And C is the length or the cost of the path. So C of X, cost of the path X. All right? Okay, so good. So now, this problem, you see, it has an efficient solution, and you all know it. It can be solved in a, what does it mean, an efficient solution? It means that if I give you a graph with n points, then n vertices, and I give you two nodes, and you need to find a path, then you can solve this problem, find the optimum, in a time which is polynomial in the size of the input. Okay, and so if you're now scaling to larger and larger inputs, and if you have graphs of millions of nodes, billions of nodes, then your computational costs, they scale polynomially. Of course, there are other problems for which this is not possible, for which if you really want to be sure, 100% sure, guaranteed that you find the absolute best solution that you can find, that's going to inevitably scale exponentially. Okay, so, and those are hard problems. Okay, so now, so this is the highlights for right now. We will focus on this case where this X is discrete and also finite. Okay, just like the graph example. Now, of course, things get interesting when X is very large. Now, think about, again, what does it mean to represent a path in there? A path could be, say, the sequence of nodes, the intermediate nodes that you cross from one start to end. That's finite. The space of all possible paths is huge if n is large. Okay, so you can have an exponential number of paths, and therefore we're in situations in which we are going to consider that it's impractical to just check all possibilities. So if you go back again to, I don't know, to this, of course, if you have that triangle, you might be able to just check each possibility, or at least up to some coarse graining, up to some level of detail throughout all the space. But if your space is has a million dimensions, then you just cannot check all possibilities, because the number of possibilities, generally speaking, let's say in this sense, the number of evaluations that you need to make, the evaluations of the cost that you need to make, scales exponentially with the size of the problem. That's a typical occurrence. Okay, so for example, here you have, for a graph of size n, you have in principle an exponential number of paths, and you don't want to check them all. We have an efficient algorithm for that, but sometimes we don't. And when we don't, we are confronted with the fact that that we don't want to check all possible values of X and see which is best. So there are various, basically in those situations that I described, in which there is no efficient known algorithm, the best you can do is give up on the condition that you're going to find the best solution. Okay, so that means that if you want the guarantee to find the optimum, then you need to be prepared to have to spend an exponential number, an inordinate amount of time. So if you don't want to spend an inordinate amount of time, then you need to somehow accept that you might find something that is good, but not maybe the best. All right? Okay, so this is a heuristic approach in a sense. So means we are trying to find algorithms that work and give us something that's possibly not optimal, or not optimal in all possible cases, but that more or less gives us acceptable, reasonable solutions in reasonable amount of time. So there are whole families of these approaches, and what we are going to start seeing today is something, a subfamily called of greedy approaches. This is not going to be very good, but it's going to be the jumping point for another thing which is going to be much better. Okay, so good, all clear? Yes. Okay, so greedy approaches. As I said, greedy approaches are a subfamily, and it's not a very well-defined family. It's let's say there's a bit of confusion about what is a greedy algorithm and what is not. The general idea, maybe, I think, is better explained with an example, and then we come back to the other slide and explain the principles in detail. Okay, so first of all, what is this? In this example, I have 13 points here, as you see. Now, this is not the graph that I was mentioning here, okay? It's not something like this. This represents, each dot here represent one possible configuration, one X. So in the mapping, this might be confusing, but we need to get used to that. In the mapping, so if you represented this problem of finding the shortest path in this way, you would have 1 point for each path, okay, not 1 point for each node. So 1 point for each path. And you see that indeed each point has its label because we are in the discrete finite case. There are a discrete finite number of possibilities that we have to look at. For each one, you have a cost, which is written on top. And the idea here is now that we need to think of a situation in which this graph here has a size, a humongous size, I don't know, 2 to the 1 million, okay? So something absolutely unmanageable. So, but in principle, it exists mathematically, okay? Also, so, and this is a situation in which you would not be able to just start from the configuration number 1 and see its cost 2 and see its cost 3 and see its cost and so on. This is not doable. Yes. Okay, so the difference is that this graph is an abstraction of the whole optimization problem. In this graph here, you can think of the nodes as, say, for example, representing cities, let's say, and the edges between them as representing routes. Okay, and then each edge has a cost here, and you're given 2 nodes, and you want to find one configuration. Okay, now that configuration is one of many possible ones. Okay, that path, yes.
Is the cost related to the configuration or moving from one configuration to the other?
Okay, so let's be more precise. So here I have one cost in this example, which was, say, EG shortest path. Okay, so here you're given a graph with n nodes and vertices, let's say, which might be cities, and with edges. Sorry. So each edge has a cost. Each path from start to end has a cost which is the sum of the costs of its edges. Okay, good enough. So here I have the green path, and each step there is going to have a cost, and the cost of the whole path is just the sum of the costs along the path. Okay, and then, okay, so this is this representation. Now, we are going to move from the left part to the right part in a sense. Now, we are going to switch to this abstraction here. So you see, X here is one path, one whole path. So the green path here, say for example, could be, I don't know, node number 6 or something. And then you look at the cost of the whole path, and you write that cost on top of the node. And here there is the green, the orange path might be, I don't know, node number 9, let's say. Well, let's pick a better example, node number 3, okay? And you look at the cost of that, and you write it on top of here, 1.1, okay? And I haven't explained what the edges are yet, but I'm going to do that very soon, okay? So in this picture here, each node represents one configuration, which in the example could be one path, and its cost, okay? And now the thing is that there are too many of these to just go one by one, okay? So we need to find a better solution. The other thing is, what are the edges? Okay, the edges here are supposed to represent this. Suppose that you have two configurations and that somehow they are close. So for example, in the case of the path, you might have one path and another in which you just change the whole path is almost the same, but you have changed, I don't know, one of the nodes. So instead of going through some node, you go through another one, okay, at some point in the path. And that, in that case, we decide that those two paths are close, okay? They are neighbors. And this is what I'm representing here with the with the edges. So why I'm doing this? Because here's the thing. Because you can be at some point, say for example 12, you might be considering one choice, one path. You have now computed its cost, and you might want to say, okay, what if I changed it a little bit? Okay, what if I yes? Exactly what I said. So you decide yourself essentially what's a neighbor, what's given a path, you decide what's close to it. And for example, we might decide that given a path, if we keep everything the same except for just one tract, okay, so we might decide, for example, that given a path, okay, which I'm going to represent somewhere like this. So suppose that there are 3 cities. This is start, this is end, okay, and these are 3 cities in the middle. And the path could be, I don't know, along 1 million, let's say, of steps, whatever. And you just decide, for example, instead of going this way, to go that way, let's say. Or maybe, you know, even better, just try to skip one of the intermediate vertices. Or, of course, you might want to say, given another possibility, could be, say, here, instead of going directly through from this point to that, maybe make a detour because it's a shortcut. I mean, going through some other node, maybe instead of going directly, you go that way, and that's somehow shorter, okay? So these things can happen. So suppose that you have decided that now, given a path, these kind of other paths, we call them nearby because they are similar, okay? We have decided that. Now, if we have made such a decision, if we have decided what is neighbor to what, in principle, now, given, and suppose that now we are at a certain path, now we can say, okay, I could start considering all possible ways in which my current path can be changed a little bit. Okay, good? Okay, so, and consider this. If you're given in this kind of situation, if you have a given path and its length is somehow, say, let's say it's order n, and you might want to consider all possible ways in which you can change it a little bit. If it has n nodes and steps, then there are going to be order n things that you can do. Okay, just one perturbation or 2 perturbations per each point in the path. So it's not exponential, you see. It's something manageable, exploring the neighborhood of your current configuration, right? Is it clear? This is important, yes?
So using this graph, you wouldn't reach, like, depending on the starting position, you wouldn't reach the optimal point.
Exactly, that's what I'm about to get at. Good. So if you look at this, now, of course, if you look at this graph, you pretty easily can find the global optimum. The global optimum is there, global minimum. Okay, good. Now, however, there are a couple of points, as you were saying. Well, there are a couple of special points, so-called local minima. Local in the sense that if you're there and you look at all possible perturbations around, then none of them improves your situation. Okay, so of course, this is true for the global minimum. You see, you're here and you look at all possible neighbors and the costs are larger. But what are other local minima according to this definition? Can you see them? 4 and 6, yes, there we go. Okay, good, good. So, so the idea now, as I said, was that we cannot just explore all of them. We need, so, but what we can do is start from somewhere and just look around, as in the sense that I said before. So basically, we are allowed two things in this scheme because the graph is assumed to be so large. We are allowed to do either of two things. Either choose a configuration completely at random, okay? And we might use that just to choose a starting point. So, but you can choose something totally at random, and that's not typically going to be very good. If you think about choosing a path completely at random, it's not going to be something that good. But then you can start to look around, meaning look at neighboring configurations, neighboring paths that are close to that, and consider those. So you start from some point, let's say this one, for example, and then you start looking at your neighbors. And now the scheme that I'm going to propose, so there are several things that you can do, okay? So immediately when I'm going to describe this, you're going to think, well, why are you doing that? This is not, obviously not, not great, okay, what we're doing. So, but what I'm going to suggest as a scheme here is, given your current configuration, just pick one of the neighbors completely at random, one. Okay, so random perturbation of your configuration. So in this example, it could be that. Okay, there are just two, you just choose one. Now that you've chosen one, you consider its cost and compare it to the one that you came from. And the rule is extremely simple. So the idea of greedy algorithms is that they are extremely, extremely general and simple. Okay, absolutely trivial. So just compare the cost from this to that. Is it improved or the same? Good, go there. Otherwise, just reject that and pick another one. So in this case, we have chosen to consider this. You compare the costs and you see it's good, okay? So now we are here. We have changed our configuration. Now we also check all possible neighbors. As you can see, we might end up in the global minimum by chance, but say that instead we had come here and chosen. So if we are lucky, we pick this and we are done. But if we are not lucky, maybe we pick something else, consider this, see that the cost is larger, reject that, say no, don't want to go there. Pick another one, we are unlucky again, we get here. Now this one is an improvement, and so we pick that. Now we are here, and whatever we want to pick around is going to be worse than what we're at, because we're at the local minimum. And therefore, we stop, okay? And we have found one configuration. That configuration is going to be a local minimum, by definition of what we have just done, because we stop whenever we have no way to go, nowhere to go, and that's the definition of a local minimum. But of course, it doesn't guarantee a global to reach a global minimum. Okay, so you could think, as I said, of medicine, which you might want to improve this. So you might think, for example, that you always want to look at the neighbors, consider all of them instead of just one at random, and pick the best. That's an even greedier approach. So this does not necessarily work. It would work, I guess, in this simple example, but in general, it might be even worse. The other thing that you might consider is just to do the following. Do this optimization once, find the local minimum, and then you don't know whether what you found is the best possible thing that you could have done or not. A simple, easy way to fix this is, well, keep that, what you found, keep that on the side, and restart from scratch. So start again, extract another configuration at random, do all of this algorithm, reach another local minimum. When you've done that, you compare it to the one that you had before. Is it the same? Is it better? Is it worse? If it's better, then okay, keep that and do another test. And you can do, I don't know, 1,000 tests. You do it 1,000 times, and you just, every time you reach one local minimum. In some problems, it might be that you always find the same. In some problems, it might be that you always find a different one, but maybe you find one which is good enough. You just keep the best, okay? Is enough. Good. So this is called, what I just said at the end, is called multiple attempt, so restarts also. So you end, you finish, and you restart again. Okay, and an idea that we are going to explore later, however, not right now, but keep it in mind for later, is that one might want to consider algorithms which are not greedy, in the sense that they don't always just, this algorithm is greedy because you only accept moves that improve your situation. So you want to minimize your cost, in a sense, always go down, always minimize the cost, okay? Sometimes it's good to consider situations in which things might get a little worse before they get better, okay? And in this example here, it might be beneficial to consider an algorithm that even if it's there, it doesn't get stuck necessarily. It might want to go over a hill, in the sense, you see, from 0.5, you might go over to 0.8 just to decrease later. Yes?
What if for each node we consider all the neighboring nodes,
Yes.
check their weights?
Yes. No, yes, okay.
Check their costs,
Yes.
and move to the one with the lower cost instead of checking them?
Yes, so, yes, good. So I mentioned this briefly. So the suggestion is look at all the neighbors and just pick the best one. In this simple graph, it would work probably, but that's, okay, so first of all, that's even greedier. That's an approach which tries to maximize even more, let's say, so to go down in the cost even faster, as fast as possible. So wherever I am, just to pick the move that brings the cost down as much as possible. That could work in some situations, but in general, it might be even worse than this one. You immediately get down to essentially to the closest local minimum. You are going to see something very, very similar to this idea in the second part of the course. But right now, I want to use this one because that, what I just described, that is a good jumping point, it's a good starting point to do what I'm hinting at here, where you actually might want to somehow go over a hill in order. So you want to somehow do moves which are not beneficial, okay, immediately, but just in the hope that later on you will get to a better situation. All right? Understood? Okay, so remember that this is an abstract representation of our graph, and that in principle, when we are going to deal with this, it's going to be huge. Okay, so as promised, let me just go back here. So what I just described, here there are a couple of other examples which I'm not going to skip because we'll see more than enough of them. So this is a type of greedy approach in which you pick an initial guess, call it x0, somehow at random, possibly. So repeat for a few time steps. Maybe you have also a number of largest possible amount of time steps if you don't want to spend all eternity. So you just pick one neighbor of the current configuration at random, say y, and then you compare the costs of the two. And if the cost of the new pick is better than what you currently have, then you set your configuration at time t+1 to be the one you just chose. Otherwise, the configuration at the next time is going to be the same as the one at the current time. All right? Good? So this is, what's the advantage of this? Well, as you can see, first it can be described in 3 lines, okay? It's usually very quick to implement and to run, okay? So it runs very quickly, normally. If you manage to do it, we will see. And it's relatively easy to implement. And it usually gives very poor results, unless you are in a situation in which the problem is easy to solve. And in such situation, it's likely that there are going to be much better algorithms than this. But this one is easy, okay, to think about and implement. And as I said, it's going to be a starting point. Okay, so this one is we are going to implement today, okay? So let's think about what we need in order to implement this, okay? So what do we need to translate this idea into code? We need, well, one way to represent the configuration X in the memory, okay? So whatever problem we have, we need a way to represent what the current situation is, our current node, okay, in the graph. Then, how to compute the cost? Of course, that could be expensive. How to pick randomly an initial configuration? How to pick a random neighbor? And this is going to be the move that we propose. So we need to write down a function that is able, given a current configuration, to propose a move in the neighborhood, okay? And then decide whether the new configuration is better, which we are going to call delta cost, so the cost difference, okay? Okay, so about this last point, just a little note. This is going to come up later. So why I said if we know how to compute the cost, then we immediately automatically know how to compute the delta cost. Just compute the cost of the new one, the proposed move, compute the cost of the old one, do the difference. Okay, that's automatic. But typically the case, because we only look at neighbors of the current configuration, so we only take a current configuration and change it a little bit in one component, perhaps, or two or something, it's often the case that the cost of the whole thing changes just slightly. So again, for example, look at this path. In this path, if you just change this path to the green detour, everything stays the same apart from these 3 edges. If you just remove an edge, again, everything stays the same apart from these 3 edges, right? So if you propose this move here, you don't want just to recompute everything from scratch. You just want to say, okay, what's the difference? The difference is only going to involve these 3 edges here. So it's generally the case that these kind of approaches are good when there's a shortcut such that every proposed move the delta cost can be computed very, very quickly. So as I said, this is an idea of this algorithm is that the algorithm is very stupid, very greedy, but very quick. And you can just run it a lot, okay? And hope to get lucky, essentially, in a sense. Okay, so this is, so there are other possibilities of greediness. As I said, it's a vaguely defined family of algorithms. There's another example that I have here, which I'm going to skip because we are going to look at it later, at a later point. But just so you know, greedy doesn't necessarily mean just what is explained. Greedy, but from now to say the next few lectures, when I say greedy, I'm going to speak about what I just explained. Okay, this scheme that I said we want to implement that. Okay, so again, just a note. There are, of course, not greedy or not so greedy approach. So just the best path from A to B. Dijkstra's algorithm is way better and optimal, essentially. So you don't want to use the greedy algorithm for that particular problem because there's an efficient solution for that. In another part of the course, we'll see situations in which we can use something called dynamic programming to actually it's another family of algorithm in which you can solve optimization problems in polynomial time efficiently and guarantee that you find a solution. So again, a situation in which you wouldn't be wanting to use this greedy approach. For some problems, no fast algorithm that guarantees to find the optimum exists. And what we are going to do for those is to start from the greedy approach that I just described and then transform it into something way better, which is called simulated annealing. Okay, so but we start from the greedy one. Good? So as a running example, we are going to use, oh, sorry, there's a, sorry, attendance. Good. So before we start here, thank you. A couple of things. First, attendance. Good. Let's see. Reload this, enable the attendance. Okay, please record your attendance. Thanks. Thanks, Davide, for reminding me. Also, there's a question by Pierluigi Mancinelli. Is it like an MST, minimum short spanning tree, I suppose? I'm sorry, but I'm not sure what you're referring to. So if you want to expand on the question, please do. In the meanwhile, I'll start speaking about one problem that we are using as an example. This is a very, very famous problem. I know that someone already wrote about it in the chat. Do we know it already? Do you know it already? Sorry? You looked at? Okay, in the computer science one part. But there are also exchange students here. Is anyone not familiar with this? I'll explain it shortly. Everybody familiar? The first example you called shortest path problem, is it a minimum spanning tree? No, a tree is a tree, a path is one line. So that minimum spanning tree is another example in which you have a problem that is an optimization problem. In that optimization problem, the configurations are all possible trees, and you want to find the best one. In the problem I mentioned, the configurations are all possible paths between two given points, and you want to find the best one. Okay, so another kind of optimization problem for the minimum spanning tree. Also, there are efficient algorithms. Okay, so using a greedy approach is not a great idea. But for the traveling salesman problem, we don't have a very efficient algorithms at all because it's NP complete. Okay, so because everybody apparently knows about this, I'm just going to fix some notation. We are going to call the nodes of the graph cities, and n is their number, and two cities I and j have going to be a distance dij, and we are going to consider only the case in which the distance is symmetric. So going from I to j is the same as going from j to I, which is not always the case in the real world, but we'll ignore that complication and take the symmetric problem. The problem is to find the shortest route that goes through every city exactly once and goes back to the starting point, which in mathematical terms has a more rigorous definition. So now we have the space, so we are trying to find so-called Hamiltonian path, a path that starts from a point, goes around, gets back to the initial point, and spans all possible nodes in the graph along the way. And so now the configuration space is all possible Hamiltonian paths. Consider how do all possible Hamiltonian paths look like. Let's think about this. So you have a number of nodes. Cities, okay? Give each city a number, 0, 1, 2, 3, 4, so on, okay? So the cities, of course, they could have names, but we are going to just say this is 0, 1, 2, 3, just list them. And now, maybe instead of waving my hands, I'm going to do something better. So consider this. Suppose that you have here, I don't know, New York and Rome and I don't know, Moscow. I don't know, Beijing. I don't know, Cape Town. And whatever. La Paz. Well, I don't know. Doesn't matter. Okay, so you have, let's say, all possible flights, let's say, with their times, supposing this is not true at all, of course, but we are going to assume that it's symmetric. Okay, so something like this. I don't know if I have all possible roots here. So what we are going to try to find is something like this. So an optimal path here would likely look something like this. All right? Well, maybe, so let's do it this way to say that this is the best. Okay. And of course, then one could consider other possible paths. Suppose that you decide to just sort the cities alphabetically. So this is city 0, this is city 1, this is city, well, this is, well, okay, not a great example. So 3, 4, and 5, I guess, right? Anyway, doesn't matter. So now the path here, what is it? You pick a starting point, it doesn't matter, maybe Rome, okay, because it's closest to us. So Rome, so the shortest path, it's 5, then 3, then 0, then 1, then 2, then 4, okay? And since we are done, it's implicit that from 4 we will go back to 5. So from the end, there's going to be the link, okay? So this is one way in which you can represent, of course, the solution in this case, but how about any other path? Any other path that you're going to consider, what is it going to look like in general? Like a list of indices of cities, each given by its index, with the characteristic that the index, all the cities are there and no city is repeated, right? So it's a permutation of all the indices from 0 to n minus 1, all right? So the space of all possible Hamiltonian paths, in this case, is just like the space of all the permutations of the cities. How many permutations are there with n cities? N factorial. Now, if you think about it a second, you'll notice a couple of things. First, that the path that starts from 5 and follows this route, it could be equivalently, I mean, we could start from 1 and do 1, 2, 4, 5, 3, 0. It would be the same path. We could go in reverse, because we are in the symmetric case, we could. So, but the first thing I said that, I mean, you can arbitrarily pick a starting point. So you have, for each path, there are n equivalent paths, okay? But that's just n factorial, so n factorial becomes n factorial divided by n, so it's n minus 1 factorial, and then for each path you can do the reverse, so it's n factorial, n minus 1 factorial divided by 2. It's still huge, okay, clearly. And so this, you can think, oh, well, maybe I can save some time by just considering a reduced number of permutations, but not really. I mean, it's still n minus 1 factorial divided by 2n is still, exponentially large, more than exponential, okay? So impractical to explore all possible paths. Okay, so how do we do this with a greedy approach? Well, as we said, we need to decide a few things. So we just said these two things. Now, this here is one possible approach that one might think about using, which is just pick a city at random. This is another greedy approach, not the one that I mentioned before. This is another greedy approach in which you start from a city at random, and then choose to go to the closest city, just the closest one, okay? From there, go to the closest one that you haven't visited yet. and just keep going like that. That's going to be, normally, that's a horrible strategy, because often, why? Think about it. That might be a good strategy from going to one point and explore all the city and reaching the end, but then you need to come back at some point, okay? And typically, if you use this strategy, and you're not on the globe, but let's say that you are on a flat map, let's say that you start from a starting point, you start moving around, you do small steps along the way all the time, you reach at some point the last city, but then you need to go back. And the coming back point is not accounted at all by this strategy. So this strategy doesn't consider at all the fact that there's going to be a last step. So the last step, if you're lucky, is going to be close to where you started from, but you really need to be just lucky. So this method is awful, okay, in general. So the other one is the one that I just showed, which means start from a random route, and then start to permute it a little bit, to modify it a little bit. So just try little modifications and see if you are improving the situation or not. Okay? Just like in the graph before, you are at a given node, you just try the neighbors. Here a node is a path. The neighbors are similar paths, in a sense that we need to define. Okay? So, as I just said, the route is represented by a permutation of the city's indices. That's going to be our working. But then we need to decide when two routes are close. What does it mean that a route is similar to another one? And there are several possible ways. So whatever way you choose on will define your algorithm. Okay? So the choice of neighbors. And there is going to be trade-offs between one choice and the other. And what we are going to use is something that works surprisingly well, even though it's not entirely intuitive. What we're going to use, so just so that a little bit of background, I know that you all know this, but this is a very famous problem because it's NP-complete and easy to define and so on. And there's been lots of work devoted to trying to find good ways to find approximate solutions, so-called approximate optima to this problem. And through, say, trial and error, people have stumbled on an intuition, of course, good intuitions. People have stumbled on this choice of moves, of possible ways in which to perturb the current path that is effective. And it's the swap paths. So just pick two edges, given a path, pick two edges, ij and lk, and swap them. So in pictures, here's how it works. Suppose that you are a path. Here is the one on the left that you're considering. And we are going to look at this path and only look at 4 nodes in the path. Okay? First, an edge somewhere, and then another edge. Okay? And notice that in this path, we are going in this direction, so close. Okay? So this is the example. Now take the move, the proposed move is keep everything the same, but swap these two paths. So from I, instead of going to J, go through L, go to L. All right? And so if you go to L, you see on the right here, that means that you are going in reverse now on this upper portion of the path, but that's not going to change anything because we have decided we are in the symmetric situation in which if you take a route in reverse, it's the same. And we end up at J, and at that point, you go back to K. And the part below here is going to still be followed clockwise. Okay, so notice that we have changed just 2 edges, 4 nodes, 2 edges. Notice that the cost hasn't changed anywhere else. So in this sense, you see, remember what I said before, that it's good for these algorithms that when you do a perturbation of the current configuration, the difference in the cost, the delta cost that you want to evaluate, you want to see if you're improved, if your situation is improved or got worse, That's efficient to compute because you don't need to compute it from scratch. You just need to consider whether these two pieces of path taken together, so if the distance between ij plus the one between lk is larger or equal than the sum of these two other distances. Of course, in this picture here, it's not. If you have this picture here, of course, this move would be rejected. Okay, you propose to do that, but you have just increased your total length and you reject this move. But if by any chance you were instead, if you swap the two situations, if you happened to be considering this situation here and then you propose to go there, then you accept the move because it has improved. All right? Good. So only 4 edges involved. Well, that's an error. Only 2 edges involved. 4 nodes. Okay, good. Okay, everything clear? So we are going to implement this. I'm going to just sketch down. Now we're going to create a file. Okay, so okay, I am in a new directory. I strongly suggest that, oops, come on. I strongly suggest that you create a new directory for this, call it Greedy or TSP or CMAN or whatever, okay? And then the very first thing that we are going to do is to create a new file. Well, yes, create a new file, save a new file, save as, without even writing anything. We are going to save it with a name, which is going to be, let's say, oh, this one, where is it? Long. Okay, this is going to be called Greedy Sketch. Okay? By the way, I have a roadmap here, so just to be sure that hopefully I don't. You were not seeing anything, and nobody told me. Please, do tell me if you don't see what I'm talking about. Okay, so here's the thing. Where is it? It's right here. So this is a scheme, okay, the greedy approach. So we want to translate this into code. How do we go about doing that? Well, the way I suggest doing that is to start from basically copying the description given in words and try to do little modifications and then start to form the general structure of the program and then filling in the details one by one. So what I'm saying is that we are going to implement a greedy approach. So we are going to go to the code and say def greedy something, okay? Not sure what yet. Okay, we are going to have a function called greedy, all right? So the first thing we need to do is pick an initial guess, okay? So we are going to say x equal, we need to create an initial configuration of some sort. So let's say that we are going to just have init config of some kind, okay? And don't worry, I mean, this is going to be a to-do, okay? So all of it we're going to do later, but right now we're writing down the general structure, translating just what we see here. So repeat for all time steps t, all right? So we have a loop, and we can do a for loop, t, where t is the time step, in a range, and the range is going to be, let's say, there's going to be a maximum number of iterations of some sort, okay? And here we are going to do the work. So as I write, as I go along, I also give names to things that I'm going to define and then maybe revise later, okay? So now what do we need to do? Pick a neighbor. So in other words, we need to say, we need to propose a move of some kind. Now, the move is going to be a neighbor of the current move. What's the current move? It's x, and so we are going to propose a new configuration of something like this, all right? Good? I've called it y here, but okay, I'm calling it x1 here, just no particular reason, okay? So we need to propose a move, and of course, to do, okay? Then we need to just look at the costs, compare the costs. So if somehow the cost of x1 is less or equal than the cost of x, so the new configuration is better than the last one, well, then the new x is going to be equal to the, we're going to accept the move. We're going to say x equal x1, right? So, is it good? Otherwise, you would say, I don't know, you see, keep the current configuration, which is just like saying this, which is completely useless, okay? So we don't need the else, all right? At this point, basically, here it says find until we find the next such that all its neighbors are worse. So here we can be even sloppier than that in the actual code. We could say at some point, I don't know, keep going until you fail repeatedly. I don't know, if you fail 1 million times in a row, stop. Something like that. Or be even more sophisticated. Instead, we're going to be very sloppy and just say, you know, keep whatever whatever happens, just keep going for a number of iterations, predetermined. And if that number of iterations is very long, then the worst thing that can happen is that you're going to spend all of the last part of the optimization stuck in a single point, keeping proposing moves and rejecting all of them. That's a waste of time, but it doesn't harm. And as a preliminary code, it's fine. Okay, so when you do preliminary code, you don't really want to really do all of the details first. Just focus on the essential. And here, so this shows us what is exactly the essential, and then we return the configuration. Return the configuration. Okay. Good. Good. Okay, I'm saving this. So this is our sketch. You see, a very simple structure, except that, of course, there's something else we need to know, the cost, okay, to do. And there are other obvious things that you might think of, like, for example, look at this. Is this necessary all the time? You can keep the cost of the current configuration and keep it around. Otherwise, you're computing it from scratch every time. But doesn't matter, okay? Not right now. We are not trying yet to make the code fast and efficient and so on. We are just trying to get as quickly as possible to a working version, okay? Something that actually does what's intended to do, and then we are going to optimize it, all right? Clear? Good. So this is the sketch. and this is our starting point. Of course, there's no mention here of the traveling salesman problem. And here's the thing that I want to demonstrate with this part of the course. This part of the course, I just showed you, just told you that we have this greedy approach, and I have sketched it in code, and you can see very well that it doesn't really assume anything in particular, or it has very, very few assumptions about the kind of optimization problem that you're trying to solve. Okay, so this is a general scheme, a meta heuristic. Okay, you give it a problem and it tries to do this, to follow this general scheme. But then, on the other hand, for any problem that you might be trying to solve, the algorithm must need to know how to do a few things. At the very least, this one, and this one. So if you have a problem for which you know how to do those three operations, then you can apply this algorithm as is. If you have a little bit more knowledge, then you can apply an improved version of this algorithm, a more efficient one. But the idea is to decouple the optimization algorithm on one hand, and the optimization problem on the other. So the idea is that we want at the end to reach a situation in which we are going to have a generic optimizer and possibly, potentially, several different optimization problems, many maybe very different one from the other, but such that you can just plug them in the optimizer and the optimizer works. Actually, to be precise, we're going to have two different optimizers and several different problems. And in such a way that you can have any optimizer works with any problem. Okay? And this is a general pattern in programming. So I think it's a good thing to see how it works, what it needs, and so on. Now, because I think this is a good place to have a break, so let's anticipate a little bit the break that we should have later, so that now when we come back, we start writing code. All right? So 10 minutes, 11:45, unless there are questions right now. Anybody? Online? No? Yeah. Yes, there's a question. Sorry. I'm sorry. Please. There's a question and I cannot. Please. Can you hear me? No, sorry. Please stop talking. I really cannot hear him. Sorry. Ah, yes. So good. Yes, there is a reason for that. So yes, good point. So let me just briefly comment on that. So the question is, I have less or equal here. I could have less than and be more strict. Okay, so what's the difference? The difference is that if you have two neighboring configuration with at least two neighboring configuration with the exact same cost, with this scheme here, you might end up going back and forth at the end. So, and with a strict condition, you can just stop at one point. But on the other hand, if you look at a situation like this, where is it? This. Okay, look at a situation like this. Imagine, let's say, that here you had a 2.5, I don't know, here, okay, in the middle. And you started from 12 and go to the node 10 and find 2.5, and that 2.5 would block you, okay? And then it would not let you reach further. So this less or equal is somehow more permissive. It has the drawback that you might end up going back and forth between different equivalent configurations, but it has the advantage that it allows you to explore more freely the space. So we're going to choose less equal because we want the freedom, and even if the algorithm keeps oscillating between different equivalent configuration, we don't care. We just pick. At the end, it's going to just stop at one, whatever that is. Who cares? Okay. So less or equal is in this case, probably a better choice, but it's a perfectly reasonable. Oh, the other thing is that actually in the traveling salesman problem, unless you have very, very, very particular situation, it's never going to happen that two paths have the exact same cost, okay? That's very, very unlikely. So it's not going to be, but good question. Okay, so what time is it? 39, 10 minutes, 11:50. Okay, good. Okay, we're about to restart. Give a few seconds for people online also to get back. Please take your seats. Okay, ready? Let's go. So, I guess some of you might be semi-familiar with versioning control systems, which means you have a code and then you have a different version of the code and you somehow keep track of the history of all you did, which is a very good practice, but we are not going to do it in the sophisticated way. We're going to do something like that, but in a very, very simple, I mean, the simplest way it's possible, which means that I'm now going to take this greedy sketch and save it in a sense for later, and I'm just going to save the file with a different name, okay? And in the same directory, I'm going to say call this greedy v0, version 0, okay? So first one was the sketch. Now I'm working on the version v0. So, and then every time we do something, let's say, significant, we're going to keep that and change version, okay? So that at the end, I will also upload all of the versions, and you can compare one to the next and see what happened, okay? Okay, good. So version 0 now. What do we need to do? Well, of course, we need to do something. First of all, we need to get inside this picture, we need to get the problem that we're trying to solve, the traveling salesman problem that we're trying to solve. And so, as I said, we are trying to do something. The long-term goal is to have something in which we have solver on one side and the problem on the other, and they somehow interact. So instead of starting writing stuff here, I'm going to basically leave this alone for now and start defining my problem on top. And so this is a good situation in which to use classes. Okay, so I'm going to create a class called cities. And this, the idea is that we're going to have an object, a cities object, that represents the graph, essentially. Okay, also, one more thing. In a realistic scenario, someone gives you the cities with all their distances, and you need to solve that. Now, because we don't have a problem instance, what we're going to do is we're going to generate random problems for ourselves to then solve, okay? So we're going to generate random problems, which means random, and the way we're going to do it, generate a random planar, meaning two-dimensional, uniform, which I'm going to say in a second what this means, TSP, traveling salesman problem. And so what we're going to do is we're going to consider a plane, so, and more precisely a square, so the 0, 1, 0, 1 square, and then we are going to pick cities in the square completely at random. So uniformly at random. And we know how to do that, right? We've already done it earlier in the course. Uniformly at random. And then what's the distance between any city and any other city? It's a Euclidean distance. So we're going to use Euclidean distances. All right? Which, of course, fulfills the requirement that it's symmetric between any two cities. Okay, so this is what we are going to do, and now we need to implement it. So, of course, this is going to be in the constructor, which, or rather, I'm calling this the constructor, even if it's not technically the right term. I'm going to have n, just the number of cities, and for now it's good enough. So just this is going to mean generate n cities at random in the way I just described. So I can just put a little check that n must be an integer, and for reasons that are going to be clear later, I want n to be at least 4, otherwise our code will not make any sense. And so we have at least 4 cities, and if this is not the case, then raise, let's say, an exception. Well, raise an exception, n must be an int larger or equal than 4. Okay, something like this. Doesn't really matter too much what the error message is. Something sensible. Okay, now given that, we want to generate cities at random, which we have already done. So I'm going to call them x. Of course, now you know right now that you need to import NumPy. And in order to generate coordinates, you do np.random.random. Actually, there's a short version, rand. It's exactly the same, so I'm going to use the short version. And so it's precisely the same as before. So this generates n coordinates for the cities, and I copy this and paste it, and just call the other one y. Okay, so now I have generated n random coordinates, the x and y separated, just like we did earlier. And okay, now these have been generated but are not stored in the object yet. So I'm going to store them in the object by doing this. Okay, everybody familiar with this? I'm creating attributes inside the object itself and just calling them x and y and assigning the. I could have done it here, self.x equal whatever, but I'm going to do it this way, nevertheless. Okay, and what's the error here? Invalid syntax. Ah, yes, sorry, I was confusing messages. Okay, this is also giving me an invalid syntax, so you know what? Here, at the very least, they're going to be the number of iterations. But also, so here I'm working in I had these 3 dots here, which were not valid, right? So now we are at least going to need the cities that we want. So an object of this, an instance of this class, sorry, okay, good. Fixed a few typos. Then I'm going to need the number of iterations, which I'm going to set to 10 by default, just any default will do. And then this here, the code is protesting, I mean, the editor is is saying that this is not defined, but that's by design because it's to do, so we'll ignore this. Okay, so a few things that we need to define, and the editor reminds us of that. All right, good. So, well, this, at least I can already run it and see that at least syntactically it doesn't have any problem. I can even run, say, I can even say cities equal cities of 5, let's say. Of course, if I now try to look at it, it doesn't know how to represent it because I haven't defined the method for that. But if you look inside cities.x, there are my coordinates, all right? Generated at random. One more thing, because this is going to be something very useful for later. If now I generate another instance, so if I do it again and I look at the coordinates, of course they come out different because it's random. Now, when you are developing code and randomness is involved, this creates a problem for reproducibility. If you're creating a code with a random instance, and then at some point you find a bug, and then you need to debug that, okay? So if you find a problem, and you want to investigate the problem, it's very, very useful to be able to reproduce the problem over and over until you've fixed it. And with this, you wouldn't be able to do that because there's this randomness, and every time you generate a new problem, a new instance, you get a different version of the bug, essentially, or maybe no bug at all. So the thing is that we need to want this to be reproducible. So we're even going to add, potentially, a seed for the randomness. So what we are going to do is add this to the constructor, and then say if seed is none, so is not none, sorry. So we are assuming that the seed is either none if not given or some integer, then np.random.seed seed. I think this should be good. Okay, and now with this, look at this, I can generate cities with a seed of, let's say, 6642, whatever, it doesn't matter. And now the cities x is this, and if I generate another instance with the same seed, I get the same coordinates. In this way, I can keep track of how this was generated. Good? Everybody on? Good. The other thing, so now we can start implementing at least a few things. An easy one would be init config. And if you look at this, init config is something that supposedly gives us a configuration, but gives us a configuration of what? Clearly, there's not enough information here. If you call a function like this, clearly it has no arguments, you see? So what kind of configuration would it return? Yes? What is the question, what is seed? The function, you mean?
Yes.
Seeding? Okay, so seeding is a way to initialize the random number generator. If you seed the random number generator at some value, with some value, from then on, the random numbers that you get are always the same. Otherwise, you're going to get different numbers every time. And so now with this trick, we are saying, if I give you a seed, please use that seed to generate the numbers. So now I can generate different numbers by using different seeds. But if I use the same seed twice, I get the same instance twice. Okay, and that's good for debugging purposes and for reproducibility. Okay, so I was saying init configuration needs to know something about at least, I mean, a configuration of what size at the very least. Okay, and therefore it's going to need to have cities at the very least as argument. So you see, here I'm imagining that I'm going to call the optimizer on a given instance of this class, and then for that instance, I'm going to initialize a configuration. And then I'm going to write def init config of cities, okay? And what I need to do is return one configuration at random. We said earlier, how do we represent the configuration of this problem? Remember that? It's here. So this is the shortest path, but we said any configuration is just a sequence of indices. And therefore, the sequence with the property that no index is ever repeated and all the indices appear just at most one, exactly once. That's a permutation. And so what we're trying to achieve here is to generate a random permutation. And luckily, we don't need to do it that by hand because there's a function. I'll demonstrate it on the console first. np.random.permutation of 5, let's say, you see that it gives you random permutations of elements from 0 to 4. So here, this is exactly what we need. Random permutation of what? We need a number here, you see? What's the number? The number of cities. Where is the number of cities? Inside cities. Sorry? Precisely, it's the length of either x or y, it's the same. But for convenience, we are also going to revise a little bit our decision and say, also store the number, because it's such an important quantity, we also store that in the object explicitly, even though we can recover it all the time. So I've added this, self.n equal n. So now I can, inside this function, I can recover not self, sorry, cities. There we go. Okay, and then I can use that here. You see? Good. And this is x, let's say, our configuration. Well, I'm calling it x, but in the general context, that's just an arbitrary configuration, so that's called x. But in the context of cities, I can call that root. All right? So a root and return. Good enough? See what I'm doing? Okay. Good. So this error has disappeared. There's still something here that tells me, I don't know, something wrong. I wonder what that is. I have no idea. This exclamation mark. Doesn't matter. So again, I can run the code and see that at least the parsing goes well. I can test init. Well, if I run the file again, I need to generate cities 5. Notice that I just wrote the first few characters and then pressed the up key, the up arrow, and just retrieved the previous command, which is quicker when you work in the console. And then I can do init config cities with a lowercase because it's an object, and it gives me a permutation. All right? Good. So now, as you might see, here as well, in the code here, there's going to be, again, the same exact kind of issue as before, in that every time you call this code is going to call init config. Init config has some randomness in there, and therefore, you might want to control that with another seed. Okay? Is it clear enough? Or no? If it's unclear, please do let me know. Oh, there's what is seed again? Just explain. Does the seed need to be a particular one or can be whatever number we want to put? Whatever number, it doesn't matter. It has no meaning whatsoever. The only meaning is that you choose a number and then if you use that same number again, it's going to give you the same problem again. Okay? The seed itself has no meaning. Okay, but here we need another one. None again. And here it's if seed is not none, then np.random seed. Okay? So in this way, we can control every problem we generate, we can reproduce it if we want to. And every time we run the algorithm, the solver algorithm, we can reproduce also what that did. Starting from, the starting point of the algorithm, which is the random initial configuration. So now things can become reproducible, right? Good. Okay, so now we have cities, we have config, we could go on, but instead of going on in implementation of the greedy algorithm, I want to be able to see what I'm doing. And so I could define a method for cities, for the cities class, that shows me, describes what's going on in the text. Instead, I want to have a plot, a graphical display, because that makes sense for this problem, right? We want to see the cities, and also given the cities, we want to see the route that we are looking at. So I'm going to define a new function, which is not one of these, but it's going to be just convenient. Define display. And display, what do I display? The cities and the route. All right? Yes?
Sorry, the last seed you put means that we can always reproduce the same permutation.
Exactly. Yes, so that the starting point of the algorithm can be is reproducible. It's some random thing, but you can do it over and over. Okay, and that only if you, in case you care, which normally is during debugging. Okay. Yes.
Why don't we define these functions and methods in the class?
That's a good point, and I'm going to do that later. That's going to happen later. I have my roadmap. Yeah, I want to do a thing. Yes, it's a perfectly reasonable thing to do. Yes, good. If we use a seed when defining the class, does it remain also for init config? Sort of, yes, but the thing is that if you initialize the class with a seed and then right away call init config, yes, you're going to get the same thing over and over. But if you define the seed and run, so if you initialize the class with a seed and then do something else and then call init config, or if you call it twice or thrice and so on, you're going to get different results all the time, unless you initialize the seed right before the random function that you're calling. This is why I'm using two different seeds. Okay, good question. Okay, so just to be clear, the seed is not that the seed stays there. The seed is used to initialize the random number generator, and then given the initial state, whenever you call the random number generator functions, like random permutation, random.random, all of these, then that's going to change the internal state of the generator, and that's going to go its way, in a sense. And then if you want to re-get the same sequence of random things again, you need to restart it from the initial state, which is seeding. All right? Okay, so just to be extra clear. So display. Well, we want to essentially display this first, and then on top of that, given our current route, see what we are doing. Okay, so how do we display this? Well, of course, we need to plot it. Import matplotlib .pyplot as plt. Now, so we need the plotting library. We need to plot the points. The points are stored in the coordinates of the object cities here. And so I'm going to extract those coordinates in this way. Cities.x, cities.y, which is just the same as here, as you, sorry, this one here. I'm going to use this pattern. This might be questionable for some reasons that I'm going into later, but I find it useful that just to give shorter names, when you're inside a function, just give shorter names to the attributes. So just create an alias so that I don't have to write cities dot every time, okay? All right, so now I can do plt.plot of what? If I do PLT of plot xy, what happens? Can you predict what happens? The zigzag, just that we saw last time, so we need to plot it with points, with dots. Actually, I'm going to use slightly nicer. So last time we saw this, to say use points, dots. I'm going to use circles, which just look a little bit nicer, which is just O, okay? Also the color, I'm letting it be the default. We can right away test it. So cities, I generate cities, and then I say display the cities. And the root argument is not there, but I don't care because right now it's not used. So I'm just trying to see if that line works. So let's see. It produced a plot, and there we go. We have our 5 cities. What did I forget? Sorry? Yeah, we're going to do that, but right now already there's something. Right, it's run it again. Change color. Why did it change color? I have to clear everything every time. Okay, so plt.clf. Okay, so now it should be good. Back to blue. Okay. All right, now the root. So how do we draw the root here? The root is going to say what we need to do. Let's think about the first thing that we need to do. We need to connect the first city with the second city, or rather city 0 with city 1. 0 and 1 in what sense? In the sense of the root. Okay, so let's just sketch down here. So a city here, a city index, how do you recover that from the root? City 0, for example, it's going to be root 0. Okay, that's the index of the first city. And then city 1 is going to be root 1. Okay, good. Now, general fact, the root has indices. These are indices of the cities along the route. Then the cities themselves as indices. So there's an overloading going on here in the sense that we use indices both to represent at which portion of the route we're in. So the 0th one, the 0th step in the route, the first, the second, and so on, and also to represent the city's indices. So the city number 0, city number 1, city number 2, the labels of the city. So you need to be careful because it's very easy to get confused and use an index, an integer, which is intended to represent where you are in the route, as instead the index of the city. Okay? So what I'm saying here is kind of important. What I'm saying here is that this, look at this at the left, on the left here. This is the path, and this path has indices 0, 1, 2, 3, 4, 5. Okay, the index of the path tells you where you are along the route in the sense how far along you are. Okay, but the index on the left, the contents of the route, is still an integer, it's still in the same range, but it represents a city name essentially. Very different meaning, same representation, very easy to get confused. So need to focus and be aware of that. That's a very common source of bugs, okay, just so you know. Good? Okay, so here, just to be clear, I take root 0 and city 1, and then, for example, if I want to plot this, I would plot, let's say, the x of city 0 and the x of city 1. So these would be, let's see, these would be the coordinates, the x coordinates of a line that I'm trying to draw, and the y coordinates are just the same with the letter y. So y here, and this plot is going to use lines, so it's fine. I'm going to say, well, yeah, we can leave it. Let's say that the color is orange, even though it's probably the default anyway. It's an invalid syntax. What did I miss? Okay, yes. So first of all, it's CT0 and CT1. Okay, sorry. So first of all, this. Then I miss a parenthesis here and one here. Okay, this should fix it, hopefully. Why not? Invalid syntax. So x of CT0, x of CT1, and one more missing parenthesis here. Good. Okay, so all the parentheses in place. So a list of 2 coordinates, another coordinate. So this should give us the starting point of so this should give us the starting point. Now I need the root. So now I need to generate the cities, but also to generate a root, which I do with init config cities. Okay, and now I can try to display that. And root 0, int object, because I called this with, I should give it root as an argument. Good. There we go. Okay, you see, first step. Now, of course, we don't want to do this. We could do this thing for all indices, essentially, but there's a better way. So how do we do, essentially, you see, the next step would be something like, don't take me too seriously, but it would be something like x of CT1, x of CT2 here, and here it would be y of, y of CT2. Good? Okay, so, but we don't have CT2. We haven't defined it. We could define it. Still some syntax error, but because there's no CT2. But the point is, we would like to do that with all the cities up to n. So do we do a for loop? We could. We do something better instead. How, you see, look at this, just this portion here. Look at just that. You can do this of CT0, this of CT1, and this of CT2, essentially. Okay? This is what I'm doing. Well, of CT1, CT0 and CT1 and so on, they are just root 0, x of root 1, and x of root 2. If you look just here, you see CT0, CT1. Okay? So this kind of thing, but we want to keep going. How do we do that with just one command? There's a NumPy trick, indexing trick. You know it? I bet lots of you. You want to have a list, essentially, or rather an array, that looks something like this. It gets up to x of root n minus 1. Okay? You want to get this, but in just one line. And obviously without the dots, because the dots don't make sense. How do we do that?
You just put the
Look at this. What does this do? Root is an array of indices, and so by the indexing rules that we've seen last time, mentioned last time at least, this here is going to be doing exactly this, and put everything in an array and be efficient. Good? Okay, so NP arrange, no. So this is the solution, essentially. So what you want to do is plt dot plot. On one hand, we have x of root. The other hand, you have y of root, and color orange. Okay, comment out this, comment out the one below, comment out this and this, Come on. Comment out this, this, and also this. Okay, so let's try. Give it a try. So generate the cities, generate the route, and display. And there we go. Almost there. What's missing? The comeback, the coming back. So here we have just connected, as we saw, we've just connected these points, but we need to say from the last one, go back to the first one. And this could be done in several ways. I'm going to do it this way. X come back is equal to a list of X. We're connecting the last point of the route, which is -1, to the first one, X of root 0. How many parentheses do I have? Okay, not enough. Yes, enough. Okay, no, not enough. And this is Y. And then I'm going to plot X come back, Y come back, color orange. Why is it? Is there a problem here? Invalid syntax. What did I do? Can you see the problem here? This, still missing one. So this closes root, this closes X, this closes what? Sorry. There. Okay. So good. This should be good, hopefully. Again, cities, root, display. Let's see. There we go. Yes?
Could you please explain why when we write x as root, yes, it
Yes.
takes only the coordinate x, but not both of them?
But not?
Not both of them, because in root you have like two coordinates, x and y.
No, in root you have indices.
Only
Yes, look at it. Root is the way we represent the path in a succinct way by just telling it the indices of the cities that we are going to get, to see along the path. So that route here says start from city number 1, then go to 3, then 2, then 4, then 0, and back to 1. So it's just indices. Okay? Yes?
Is it correct to say that now we are working inside one single node?
Yes, so this route here is one configuration, which in the abstract representation that we had before, that I don't see anymore. Yes, so in this picture here, it would be one of the nodes there. Okay, good, with its cost, which we haven't defined yet, but it's going to have its cost. Okay, so yes. Well, you could be more explicit if you wanted to say draw it with lines, even though it's useless. So you could do it this way, just so that you know. If you want to really tell it use lines, you can use this. So just like this is circles, the dot is dots. And also color, you can abbreviate it if you want by just C. Okay, and this should work. Oh, sorry. And this should work there and display, and it still works. Good. Okay, and what's left? I think, yeah, so let's go here in greedy, and now, well, this to do is done. Okay, done. And then after that, we might immediately call display cities and then X. Good. So F5. Now we can try, let's close this. We can try to run greedy, it's going to fail because if it reaches this point here, you see, you expect it to fail here. But still, we should at least get up to here. So we can test that. Greedy of, well, first you generate the cities, and then you do greedy of cities, and then the seed, let's say it's whatever, 813, just, okay, and of course, proposed move is not defined. You see the error is exactly where I was expecting it. In the meanwhile, it has generated something, a root, a problem in the root, which is very, of course, very non-optimal because it's random, but let's, you know what, from now on, let's create something a little bigger, let's say perhaps at least 7, but let's say 10, okay? And then there you go, an initial root, which is completely random and of course very, very not non-optimal. Good, so this one here is our version 0. Okay, we have done some work. We have reached a point where at least we can have a problem to solve, and we can see how it's going. So we save now the file with a new name. So we want to keep that version 0 around, and I'm going to now change the name to the file to v1. Good? Okay, so v1. V1, well, let's go then and look at our to-do list in a sense. So what's next? It's proposed move, right? So we need now to have a way to propose a move. What does proposed move look like in this sketch? It looks like we give it a current configuration, and our code is going to propose to us a new configuration which is close to the old one. Now, def propose move, and then propose the move with some root. Okay. Okay, so let's think about this. Going back to the slides. Here is what we want. We want to pick 2 edges at random in the current root. Okay, so this is our first task. Pick 2 edges at random. Now, how do you pick an edge at random? An edge has 2 indices. In this example, it's I and j. How do you pick one edge at random? Any suggestions? Yes?
Take a random index and take the neighbor index.
You take a random index and then you look at the neighbor. So good, but we need not get confused. It's related to what I said before. You pick a random element in the root, not a random city, a random position in the root. Okay, so this is important. So this is going, the first edge is going to be some edge along the root. And so we pick an index inside the root. But it's going to be a root index, an edge index, not a city index, okay? So here we can say the first edge, for example, is going to be np.random.randint. Okay, so how does randint work? Let's go to the console for a second. np.rand.randint. Randint. Now this, if you give it random, np.random.randint. Okay, so if you do this, it's going to produce integers in the range between 0 and 9, okay, which is exactly what we want. And it's different from the Python's random module randint. If you know about that, that module by some weird accident gives you also the last element. So Python random.randint would give you also 10 occasionally as a value. But np.random.randint just gets up to 9. So you can look that in the documentation, of course, and it's what makes sense. So a random integer in n, because the root is length n, but where is n here? We don't have it as an argument. As you can see here, there's a problem. So in propose move, we can, well, n is just the length of the root. Okay? And so E1 is just now a random integer, but it's an integer along the route. We need another one. So, sorry, what is this edge representing? This edge represents the two cities. So the first city would be root E1, and the second city would be root E2. Okay, so this is an edge between these two cities. Okay? Good?
What if E1 is 0?
Sorry?
What if E1 is 0?
Ah, sorry. Just, it's not these two cities. It's E1 and E1 plus 1. Yes. Okay. So this is, sorry, say again.
Yeah, I was wondering what happened, like the random generator gave us 0 and so E1 is equal to 0.
If E1 is equal to 0, there's no problem because that means the first city in the root. And so E1 represents the first edge in the root, the first step, and it's the step between the root 0 and root 1. Now there's another problem here instead. What if E1 is equal to n minus 1? So what if you get the last city? Then if you try to do, where is it? If you try to do this, then you go beyond the list. But what's the next city after the last one? It's the first one. So when what you pick is the last one, there's a special case because that needs to represent the edge between that node and the first one. Okay, so let's keep this in mind. Now, but as you can see, there are n possible edges in the root, and here we are picking one at random. Now, of course, we're going to pick a second one at random. Okay, so this is going to be an edge between these two. And so our first city, let's say, our city one, let me see, what did I call it, city 1 or city? No, okay, so it's not needed yet. Okay, so let's keep going, sorry. But it's written down here. The first city is this one and the second city is this one. Okay, so now we have extracted two roots. Now what we need to do is create a new root which looks like the one on the right with a swapped thing. Okay, so let's think about how this works. Now, this is not at all. There's a question. What is the difference between display and plot show? And NP random choice would be easier, I think. So, okay, the difference between display and plot show is, I mean, the display is a function that we defined ourselves, and plt.show is a function that just shows you the current plot in case it's not already shown. And also about the second thing, NP random choice would be easier. I mean, I don't think so. It would be a possibility. I don't see why it would be easier. But Anyway, if you want to elaborate, or even right now or in the forum, it's fine. Okay, so I was saying, now we've chosen two edges, and let's make an example. Suppose we have some cities, and just let's say, I'm sure I need at least 7 of those to demonstrate. So these cities, let's suppose let's suppose that they have indices like 3, 2, 6, 0, 1, 5, and 4. Okay? And suppose that our current route is this one. Okay? So our current route is 3, 2, 6, 0, 1, 5, 4. Okay, now, suppose that I've picked 2 edges. Now, suppose that E1 is, let's say, E1. And E2 is, again, a number between 0 and 6, and it's going to be maybe 4. Okay, let's see how it goes. Okay, so what does this mean? What are we doing in this situation? Suppose that your random number generation has given you this. What does this mean? Look at the numbers that I wrote here are city names, okay? But the root numbers, the current root numbers are this: 0, 1, 2, 3, 4, 5, 6, okay? Clear? Good. So E1 equal 1 means that E1 connects the first node in the root, the number 1 in the root with the next. So E1 is this one. Good? And then 4 means this one. This is E2, okay? Good? So we've selected these 2 edges, and now we need to swap them, which means that the route used to go this way. Okay, so this was the old route, and now I want to swap them. So just like in the figure, when I start from the node here on the top, I get to the node on the right here, and before we get into E1, I'm going to swap it to the start of E2. Okay, so this is going to be the new edge. And then from there, I'm going to go in reverse until here. So I've also reversed the directions here. Can you see this? That I had these 2, I swapped them. So let's see how this looks like then, the new route. So new route, the proposed one. Let's see what it becomes. You start from the top, which is 3, which is unchanged. Then you get to 2. At this point, you get to the node there on the bottom, which is 1. Then you get to 0. Then you get to 6. And then back to 5. And from then on, you're back on track. And so from 5, you get to 4. And from 4, you get back to 3, but we don't write that. Is it clear? I just followed the thing up to the change, and then the new edge, and then the little piece in reverse, and then the other new edge, and then back. Okay? And so if you look at those 2, what changed here is these 3 nodes here. You see? Everything else is the same, and this is the only part which is affected. Can you see it? How is it affected? Well, you can see and think that the first 2 are just exchanged. But really, if you think about it, and even if you do it yourself, I encourage you to do it yourself. Take the same example and use E2 equal 5, okay, and do the same drawing. And then try to see, in the case E2 equal 5, what the new route would be like. Now, if you do that, you would realize that what happened is that you change one more piece in the original route. So instead of changing 3 nodes, 3 elements there, you change 4. And that the operation is just of reversing a piece of the route. You just reverse it, up, top, down, okay? And this corresponds to the fact that the piece of the route there at the bottom has been twisted in a sense, okay? Good? So this is the twist operation. The swap path operation is a twist, and that in our representation, that translates into taking a bit of the route, a piece of the route, and changing like that. Okay, up, down. And so we need to be precise here and look at the indices. So the indices here are 0, 1, 2, 3, 4, 5, 6. Now look at what happens. The indices that have changed are 2, 3, and 4, which happen to be E1 plus. So this is the first index that changed is E1 plus 1. It's the next one after E1. Because you see, look at the route, the first node up to the node that started the edge, you're still doing the same path. But then you change, when you go to E1 plus 1, you change. And the last one here, 4, is exactly E2. All right? So what we need to do is select a piece of the route between E1 plus 1 and E2. And change that, reverse them. Okay? Which in code, you do this way. So you have the route. How do you pick the elements between E1 plus 1 and E2 included? It's a range. You can use a slice. You can say go between E1 plus 1 and what? Do I write it like this? You need the plus 1 because in a range, the last index is always excluded. So this is the thing that we are trying to change, okay? And so this is going to be equal to something. To what? To its own version reversed, which you could do some ways. You could write it like this, I suppose, if you really, I mean, this is some sort of the lazy way. So you take the same thing, but then you revert it, and one way to revert it is doing this. All right? Now, this may or may not be readable to you, but it's also a bit wasteful. Instead, I want to use a better, what in my opinion is a better way, which is just take the same route, but start from 4 and end up at 2 and just go in reverse. So walk the route from this piece of the route, walk from the end to the top. Okay, so what does this look like? It looks like something that starts at E2, ends at E1 plus 1, and in steps of -1. Okay, so start from the bottom, which is E2, end up at E1, well, plus 1, but then there's a problem there, and get to the bottom. Okay, so I'm almost done. I just want to say that this is wrong because there's the same issue as before. So the end range is always excluded. Last range is always excluded, but since we are working in reverse, essentially you give the range as this plus this plus this, and the end point is this one here. Okay? So this is the basic thing. So actually, this would be a way to copy the root in place. So we want to return a new root, so we're going to do new root equal copy, well, or root.copy, so create a copy of the root, and then swap the thing and return it. Okay? Good. We can have a look if that actually works. We can say, let's say root. Well, first cities, then root, and then this is the root. And suppose that, again, I have E1 equal 1 and E2 equal 5, let's say, and say root of E1 plus 1 colon E2 plus 1 equal root of E2 colon E1 colon minus 1. Okay, there's a plus 1 here that I forgot. Good. So now if I look at this new root and compare it to the one before, we see that 8 and 6 are the same. And then you have this 1, 2, 3, 4, 5 up to here, actually up to here. 9, 5, 2, 3 has become 3, 2, 5, 9. And the rest is the same. 0, 7, 1, 4 is the same. So maybe you can see it better if, yeah, okay, so this is the piece that changed. Okay, now I think the time is up, right? Okay, so we'll finish this, of course, next time. This proposed move is not done yet, even though we're almost there, and this was the most difficult part, essentially. All the rest is going to be easier. Yes, there's a question?
You also would have to avoid that choose two numbers, which so like.
Yes, exactly. That's why I said it's not done yet. So the bulk is there, but it's still not working well. Why? Because there are several things that may happen. One is what you said. Suppose that you say you pick the same edge twice. What happens? I mean, it's not a real move. What happens if you happen to choose E1, which is larger than E2? I mean, that what I wrote doesn't work. There are other situations like that. Okay, so but we have a bulk. I mean, we have something that works, and then we just need to fix the details, which is a good way to go about. Okay, start with a simple situation, make your life easier, find the solution to the hardest thing, and then fix it. Okay, good. Why only one? Okay, I'll stop the recording.